Okay, looking at section 3.7, the optimization section, and this is probably about the third day we're on this, so it'll be our wrap-up day. We're going to look at a couple more difficult examples today involving minimizing and maximizing or optimization. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? And here is our equation, and I have gone ahead and graphed it out, and it is a parabola facing downward. No big surprise there with the vertex up there at 0, 4. We want to find a point that is closest to our point 0, 2, and if I just kind of sketched over, it's going to be somewhere in this vicinity. I suspect there'll be also a point sitting over here. And hopefully we gather both of those points through our process. So we should see that evolve as we go through this. Now, usually it's all about writing some equations, isn't it? So we've got y equals 4 minus x squared. Perhaps we'll want to use that. If I'm looking to bring this distance as the closest, I really want to minimize this distance. And in order to calculate distance, I need the distance formula. So distance formula we recall as being x minus x1 quantity squared plus y minus y1 quantity squared. And we've got the 2 points labeled there, so let's just go ahead and write our distance formula here involving these 2 points. So I'm going to say I've got x minus 0 quantity squared plus y minus 2 quantity squared. And we could simplify maybe just a little bit. So we've got x squared plus y minus 2 quantity squared. I'm not real thrilled about having the 2 variables in there. And since distance is what I want to minimize, this will be the equation, then the distance formula is the one I'm going to be doing the derivative of. So it'd be best if we can get it down to a single variable. And the way we're going to accomplish that is by utilizing our helper equation over here, right? And notice how we don't have much work to do. It's already solved for y. So let's substitute and get our formula in terms of x. That's why I went d of x is equal to the square root of x squared plus, now substitute for y. We're going to substitute in 4 minus x squared minus the 2 quantity squared, just substituting for y. Perhaps we could clean this up just a little bit, and we've got x squared plus 2 minus x squared quantity squared. It would not be the most difficult, would it, to square that out and combine stuff, so maybe that would be a good approach. Squaring something, we'd have the first thing squared minus twice the product of those two, and then plus the last thing squared, so that's going to raise us to an x to the 4th there. And we can pull our x squareds together, so we've got an x to the 4th, a minus 3x squared plus a 4 underneath the radical. That is our d of x equation. So now what we want to do is come in and minimize this. Minimize the equation. That's not even close to spelled right, is it? So I'll try again. Minimize, got it. That equation. So we want to take the derivative of that. If I really think about it, what I need is really to minimize the inside equation, and that will cause the square root of that to be at a minimum. So let's just work with minimizing the inside stuff, and that should be sufficient. So I'm just going to say f of x is equal to x to the 4th minus 3x squared plus 4. So then f prime of x is equal to 4x cubed minus 6x, and we want to find where this is equal to 0. So 0 is equal to, let's pull out a GCF of 2x. That'll leave us 2x squared minus 3. And really you have two factors here. Don't forget that first one. Either x is 0 coming from the first factor, or we set this second factor equal to 0, solve it, and keep working towards that end. I'm sure you're working along with me. And I ended up with plus or minus the square root of 3/2 as well as 0. Not completely confident that all three of those produce a minimum, so I am definitely going to consult a sign chart on this one to be certain. So we get the square root of 3/2 negative over here and the positive square root of 3/2 on the right. We're going to take this into our derivative function and test some values. So this is like 1.5. If we tested, well, 4/2 would certainly be larger than 3/2. So I could test out -2. I could test out -1. I could test out 1. And then I could test out 2 as my testing points. And I think once you do this, just to save some time, it's going to turn out to be a negative followed by a positive, negative, and positive, which indicates to us that we've got a decrease, increasing, decreasing, increasing function for our original function. Thus, we have a local min and another local min. There is one local max happening at that 0. So 0 would not be the one we're interested in. That makes sense. 0, 4 was a max. That's the farthest distance away up there. Remember, we were just, and we're just looking, were we just looking at on the point 0 to 2? So, I forgot about that. We really aren't even going to look over here, are we? On the left side. So from 0 to 2 as our interval of interest, we can really just zone in on x being equal to the square root of 3/2. So the x value is that. What is the y value? Well, that's a question mark. Let's simply come back to that initial equation where 4 minus x squared showed the relationship between x and y. So y is equal to 4 minus the square root of 3/2 quantity squared. Thus, squaring the square root will take that off our plate. So we get 4 minus 3/2, and that will leave us with 8/2 minus 3/2 is 5/2 or 2.5. So our point that is closest would be the square root of 3/2 comma 5/2. And kind of looks reasonable, doesn't it? All right, let's try another problem. These are definitely kind of fun problems and somewhat practical, I guess. It says I'm a mile out in the ocean, maybe that's not so practical, and wish to get to town, a town 3 miles down the coast, which is very rocky. I need to swim to the shore and then walk along the shore. What point should I swim to along the shoreline so that the time it takes to get to town is at a minimum? And we also know that I can swim at 2 miles per hour and walk at 4 miles per hour. So I'm walking, twice as fast as what I'm swimming. So there has to be a point. Here I am out in the ocean, a mile from the shoreline. And so this is our shoreline, isn't it? And here is us, or, we're out here swimming, bubbles coming up. And where should we head? Do we want to head, close in? Do I want to swim quite a distance? That's really the question that we need to answer. Well, let's just let that be a variable, x. And from there, if I swim to this point, let's mark this as our origin. So there's 0 for us on the shore, directly in from me when I'm sitting out in the ocean. It would be perpendicular to the shoreline. Now, x is the distance I'm going to be swimming, and then I'm going to walk on land the rest of the distance. So I'll be walking, if I swim x, I can then state I'm going to be walking 3 minus x miles. And I guess what we need to do is create some equations, correct? You know, this x here, that's kind of a, I want it to be equivalent to the shoreline of x, but what I'm really swimming, I need to mark up here, don't I? Because that's going to be my swimming path. And the distance for that would be the Pythagorean theorem, 1 squared plus x squared would equal c squared there. So really 1 plus x squared then square rooted would represent the distance that I'm going to swim. So my total distance covered is going to be comprised of the square root of 1 plus x squared plus my walking distance 3 minus x. And I want to get there the fastest. I want to minimize time. So it appears to me this is really going to be the helper equation. And our primary equation is going to deal with time. So the time it's going to take will be the distance, 1 plus x squared, multiplied, this would be in miles, wouldn't it? Let's get some unit labels on here. In miles, and then I can swim at 2 miles per hour. So there's 2 miles per hour. Notice the miles will cancel, leaving us just a time amount, hours, plus 3 minus x, this will be in miles, divided by 4 miles per hour. And once again, you're going to see your miles canceling and the hours will flip over and be a numerator value. So there we have time all structured out for us. And that is what we're going to want to minimize. So we want to minimize our time. Thus, that's where we're going to take our derivative, right? So we're going to have time prime. So t, it's all in x's, that's good. So t of x is equal to, can't really do a lot. I can pull that 1/2 out front, and then I'd have the square root of 1 plus x squared plus, since this is, you know, a nice fraction with a single denominator, I always think of it as that type I really love, so I can have 3/4 minus x to the 4th, or 3 over 4 minus x over 4. And now that sets it up real nice for a derivative to be taken. And we're going to have this 1/2 multiplier coming along. The derivative of square root is going to be the prime, so 2x, chain rule guy, and then 2 over the square root of 1 minus x squared. Remember how it's 1/2 and then that square root drops to the bottom. And then we've got the chain rule. Plus the derivative of 3/4 is 0, of course, and the derivative of x over 4 is going to be simply the 1/4 multiplier there. And straightening this out a little bit, let's see, we can cancel 2's there, and t prime of x is going to equal x over 2 square root 1 plus x squared minus 1/4. We want to minimize this, so we're going to set this equal to 0 to find our critical points, our critical values here. And 0 will equal x over 2 square root 1 plus x squared minus 1/4. Let's add a 4th over, and that's going to give a 2 square plus 1x. Got it? Cross multiply. 2 square root 1 plus x squared equals 4x. Divide both sides by 2, and we get square root of 1 plus x squared equals 2x. And from there, did I lose an x squared? I feel like I did. Nope, I didn't. Okay, let's just square both sides. So let's come in and square both sides, get rid of that square root, and we'll get 4x squared. There's my squareds coming in. I was hoping that was going to happen. And then we can put our squareds together, which will give us 3x squared, and divide by 3, and we'll have x squared equals 1/3. X equals plus or minus the square root of 1/3. And since this is a time function or a distance function, x is a distance, we cannot have negative distance in this case, so we will just simply work with the positive 1/3. And that is approximately 0.577 miles for the distance that we should target on that shoreline. If you come back up to our picture, it definitely shows us where we want to head. This would be that square root of 1/3, which is approximately a little over ½ mile. So 0.577. Now, if you simply put, in your x value, you are going to come up with the distance that you swim as well as the distance that you walk to finish that problem. Very nice. Okay, I have homework set up for you, and it is the worksheet on optimization. I'll create number 3 and number 5 are a little tricky in setting it up, so I think I'll do a quick video on that and post that to Schoology if you'd like to watch that. That may help you get things set up. Very good.